Good morning. My name is Colin Gench from Retrotec. This webinar is intended for people that are taking who want to take our level 1 certification, or people that just want to learn more about this. This particular webinar is going to focus a little bit more on ISO than NFPA. We have a huge preponderance of NFPA folks on there. Good to hear from you. We have many people on the line today on this webinar, so I'm really thankful for the success of it and for all of you attending and so on. Suffice it to say that everything that you have to do for ISO, you also have to do with NFPA. The fundamental difference is that ISO's philosophy is you cannot use enclosure leakage for venting, or you cannot, but typically they design them so you don't use them for venting. Whereas in NFPA, if we design the enclosure correctly, we can use enclosure leaks for venting. So that's the main difference. The ISO standard also requires that you hold your minimum concentration up to 90% of the enclosure height, which is another huge difference, which tends to make the enclosures extremely tight. So those are the fundamental differences. The rest of the material that I'm going to run through is going to be pretty much the same. And if I have time, I'll whip over to my NFPA presentation and show you a few extra slides that relate specifically to NFPA. So the ISO 14520 2006 edition, some comparisons between that and the 2000 edition is that they've gone to a wide interface model, which decreases hold time by 25%. NFPA has not done that, so that the hold time with NFPA tends to be quite a bit longer. As I mentioned earlier, ISO requires protection to 90% of enclosure height. NFPA does not. It requires protection to the height of the hazard in most cases. And there is an error in the 2006 version. E3.4.2 should read F equals 0.15. It reads 0.5, which causes that whole paragraph to make no sense. For those of you, the NFPA folks out there who do not have the 2012 version of NFPA 2001, I would recommend you get it. The 2008 version has pretty much the same stuff in it, except there were literally hundreds of errors. I rewrote the entire section that year, and the person in NFPA who was in charge of it was in the process of leaving, and it didn't really get the attention it required, and the person who took over it clearly didn't understand, and it's a total mess. And you really need to get the 2012 version. In the 2012 version of NFPA, there were a few cleanups that we did that made the test easier. One of them is we eliminated the need to take temperatures, which makes virtually no difference whatsoever. So we cleaned it up, made it a bit easier. So there's a question of what the wide interface is. I will show you a wide interface a little bit later. Both standards have a section in them that require that the enclosure have sufficient strength to contain the agent discharge. And the big question that people ask is, well, gee, how do I know how strong the enclosure is going to be? And I will be touching on that as well. But suffice to say that you really have to know or be able to specify enclosure strength. And that's a new thing, which actually is required in the 2008 version of NFPA. I'm not sure if ISO always required it, but it certainly does now. About 8 years ago, we started a research project that looked at peak pressure, and the team included every major manufacturers. It went on for 5 years, and the final round, which was a few years ago, netted some very good data for peak pressure and also for verifying the hold time formulas. And there was a researcher at 3M and myself spent 2 or 3 years modeling the wide interface that we'll talk about later, and I could probably talk about it for a week and bore you all to tears, but I won't, except to say that we do understand exactly what happens with peak pressure in enclosures now. We have massive amounts of data, and that has worked its way into the new version of the ISO standard when it comes out, interestingly enough, for hold time, and is also given us some very good results for peak pressure that are being used in the FSSA formulas or the FIA formulas. The data is pretty much public knowledge, so Retrotec uses it in its software as well. The primary determinant of peak pressure is the leak to volume ratio, which is measured by the door fan. What was unique about our research project was that it related the door fan test over a wide range of enclosure leakages to the peak pressure, and this was the first time this was ever done before. The data from the past all showed a whole bunch of data in one clump in the middle, and we were unable to determine the shape of the curve. This is an inert discharge, a very short spike, followed by a trail off, and it only lasts for, as you can see, about 1 second or so. Very characteristics of inerts. All the inerts perform pretty much the same. The data or the peak pressure formulas might differ by 1 or 2%. The conclusion I came to was that all inerts pretty much, whether they be argon, argonite, or whatever, even CO2, not liquid CO2 but compressed CO2, tend to perform pretty much the same way. So the yellow line that we have on this graph was the data that we took, and the dashed lines were all the peak pressure formulas that were being used up until that time. And you can see that in this area here, which is our area of interest, these are our areas of interest for a 10 to 20 minute retention time for a typical enclosure. In the area that we're most interested in, the peak pressures that we're getting are significantly greater, 2 to 4 times 200% error with this particular formula, which is a very popular one, and some of them are 400% more peak pressure than the formulas that were being used at that time, in fact still are. So you'll find if you use a lot of manufacturers' peak pressure formulas that it will very, very sincerely underpredict peak pressure. In some inert discharges, we have a different curve. This is the typical characteristic curve, and this is a curve with pro inert. Every major manufacturer now has some kind of regulating valve. Tyco has one, Siemens has one, and they all seem to produce about the same results, roughly half the peak pressure with those inerts, which decreases the size of the vent if you use one by half, roughly. Halocarbons, or chemical agents as some people call them, have a different characteristic. They tend to go to a negative pressure during the first period of the discharge and then a positive pressure afterwards. And the depth of the negative spike has to do with humidity, so we now have to understand what the range of humidities will be for an enclosure to predict the range of peak pressures that will occur. And this red line here shows what the factor would be, or the humidity correction would be for different humidities. So in this case, we did all of our testing at 40% relative humidity. We blew down the enclosure so that the test enclosure so there was exactly 40% relative humidity. And then we did some tests at high humidity and low humidity so that we could find the rough shape of this curve, so that as the humidity goes down, we have to use a multiplier to increase the peak pressure that we'll get, and that's all taken care of in our software. Inerts have virtually no effect, or humidity has no effect on inerts, and they can be ignored. And this is the action, this is the reason why. Here we have two halocarbons, and we're showing the extreme pressure or temperature drop over a period of about 5 or 6 seconds, and that's the reason why we get this huge negative spike, that we very, very rapidly cool a room. We have a massive amount of contraction, and this causes the negative pressure spike. Here we get a little bit of cooling within an inert, not enough to cause any negative spike whatsoever because it's so gentle, and it happens over a prolonged period of time, so that's the reason why. And this is a characteristic curve for Novak, which is generally a very big negative spike. It has a very high degree of heat absorption, which is one of the reasons why it's so effective, and it has a very big negative spike, as you can see here, almost double the size, sometimes even more, double the size of the positive spike, which typically is caused by the nitrogen blowdown in the tank. So from a design point of view, just a quick review here. The first thing we need to do is to specify the enclosure strength. Then we need to determine the necessary leak to volume ratio, and then to estimate the peak pressure based on agent type, valve discharge, and the leak to volume ratio, and then to size vents if needed. Now, for ISO, you can forget about the if needed. They always put in a vent for ISO, or usually the European model. For the American model, the NFPA testing goes on in North America. They generally install a vent if they determine that the peak pressure in the enclosure is going to be excessive. So there's a very big difference in philosophy. I will later show you a new feature in our software that will do all this for you. It's meant for the designers. It's a great tool for understanding how this works, and I'll run that new section of our software, which is still in the dev phase, and give you an idea as to what that looks like. There we go. It tells me to run FanTestic Integrity, so I'll do that. I'm going to bring up my dev version, which is the same as your version except for the peak pressure, I'm sorry, except for the designer part. So I'm going to drag this over if it will let me. So there we go. I've superimposed FanTestic Integrity over top of my previous window. So what I'm going to do here under Tools is go into Venting Calculator and drag the venting calculator back onto the screen. You won't find this in your software yet. It should be there in a week or two. Prior to this, we had an Excel spreadsheet that attempted to do the same thing. There are still parts of this that are in development. We're adding information to it all the time. And as I walk through it, I'll tell you what those areas are. We've got units here, metric imperial. We've got another unit that's called mixed, which is pascals and feet and inches and so on. And so let's just go through this and take a look at what we've got here. This one is a fixed window size, so we can't actually expand it, unlike Enclosure Integrity. So hopefully you can see that. I'm not sure about your resolution as to how clear it's going to be. So let's just start out with imperial, and venting equations that we're using here. We're using FSSA formulas, which is the data that is generally accepted by the industry for the research project that we did, and FSSA's put their name on it, which is fine. Manufacturers' equations will vary a lot, as you will see, and we're going to change the standard to NFPA 2012, and we're going to look at the descending interface model. We'll take a look at argonite and inert, and let's toss in an initial concentration here of 40%, discharge time of 60 seconds, temperature during discharge of 68 degrees Fahrenheit, and enclosure volume, let's just put in a round number here, 30,000, that should be cubic feet. and enclosure height of, let's just put a round number in here again, 10 feet, lower leak fraction 0.5, performance criteria. Now here we have a value called the enclosure pressure limit, and I should be showing you a table later that will give you a list of enclosure pressure limits, the typical ones. I think 500 pascals is a decent value. If you have a well-constructed wall that has two sides on it and it's held in place top and bottom, it will generally hold 500 pascals really well. What I was able to do with my door fan, just to convince myself that these enclosures would hold 500 pascals, is I took one of our new high-power fans, I cranked it up to 500 pascals and gave the wall a thump and said, seems to be holding it just fine. So I've actually experimented with this, and a wall that is poorly built might start to crack at 500 pascals. And the type of wall that would be 2x4, single-sided, not attached to the top, like a typical wall that might have a suspended ceiling sitting on top of it. If you were to give it a shove, you'd feel it wobble back and forth a bit, you know, that kind of thing. So, but clearly this is something that has to be figured out in the design phase. So I'll show you the table that I use later. And 500 pascal wall, 2x6, sheetrock on both sides, pinned to the floor and pinned to the slab above, and should have no problems holding 500 pascals. So as far as the minimum protective height is concerned, let's put that in at 7.5. That's pretty common. Oops. There we go. Sorry about that. What you were seeing were actually slides of the of this, and I managed to click on the PowerPoint foolishly. It's a little early for me. We're on the West Coast, so I had to get up at 6 o'clock this morning to get organized. I haven't had my first coffee yet, so hopefully you'll forgive me. So here we are. Minimum protected height is set at 7.5 feet, and the hold time is set at 10 minutes. So we're going to calculate, and it's saying that for this hold time of 10 minutes, the enclosure cannot be more than 1,356 square inches. So this is the maximum amount of enclosure leakage that you are allowed in order to get a 10-minute hold time. The chances are, the chances of you tightening the enclosure to get exactly 10 minutes are rather remote. So usually what I do here is I'll put in a 15-minute retention time and recalculate, and you'll notice this value drops down to 900 square inches. So what it means for you NFPA folks is that we can probably rely on around about 900 square inches of leakage. So for NFPA, given that we have 900 square inches of leakage, and we use all of that leakage, let's say we're going to use 100% of that leakage for venting, we still need a vent. So for the ISO folks, if we set this at 0, meaning we're going to use 0% of the enclosure leakage for venting, we're going to need a vent that has 1,734 square inches. Now, if we want to change various aspects here, like let's say, for example, we want to change the concentration, we'll notice that right away we see that that value is dropped to 1,300 square inches. If we want to increase the discharge time, we notice it drops again. So with discharge time, generally if we double the discharge time, we approximately have the peak pressure, so we have the hole size that we need. It's not a linear relationship like that, but it's a good way to look at it. Again, for your NFPA folks, if we have a suspended ceiling, we can say, aha, well, I can do a below ceiling leakage area test. I can set this at 0.25, recalculate it, and here you'll notice that if we were to use 100% of the enclosure leakage, we don't need a vent at all. So by playing around with this, you can see how you could design an enclosure so you don't need any venting at all. So how this would work is the enclosure would be built and the leakage distribution would be measured, and it would be tightened up in the bottom half of the enclosure until you got the leakage down to the required amount as shown here, in a ratio of 0.25 lower leak, 0.75 upper leak, and that would give you both the retention time that you're looking for and would not require a vent. For the ISO folks, since we're using 0% in most cases of the enclosure leakage for venting, we still need a vent, unfortunately, no matter what you do. So we're just going to touch on PRVs for a moment. A lot of you aren't aware of the fact that there are what we call dual-acting PRVs, PRVs that open in both directions. They're a little bit, well, maybe twice as expensive as single-acting PRVs, but they're well worth it. The installation cost is reduced, so it's a new group of products that are out there. So this is what we call the NFPA Sharp Descending Interface. The 2000 version of ISO used this. They then changed it to what they call the ISO wide interface, which, as you can see here, it starts at time interval 1, 2, 3, it could be minutes or whatever, and the concentration goes through an increasingly wider and wider gradient. We actually found that doesn't really occur, and the ISO the ISO wide interface formulas are way too conservative, and it requires a lot of excessive tightening of the enclosure, which is not necessary. We've made changes that will occur in the next version of ISO, but we're still stuck with this wide descending interface right now, which requires a lot of excessive air sealing. The NFPA side, the formulas that you're using are actually pretty accurate, and we didn't go down this route, fortunately, and have saved ourselves a lot of time. So this section here, 7 options to reduce the size of the PRV. For the NFPA folks, these 7 options can be utilized to eliminate the need of a PRV altogether. Again, bear in mind the ISO philosophy, or the European philosophy, is you always need a PRV. You can never rely on enclosure leaks because they think somehow they will disappear. I've never seen that happen, but that's their engineering choice. And the NFPA folks have a slightly different philosophy, that their enclosure leaks there, they probably will do nothing but get bigger, so we can rely on them for venting. So let's take a look at first one. Aha! This is a very important table that we have here. This is the only study that's really been done. I think it was done by Kidde Fenwal probably about 10 years ago or so. It shows 2x4 studs, 16 inches on center, and it can handle 13 pounds per square foot. So 13 pounds per square foot is around about 700 pascals or so. And that's only a 2x4 wall. There's a fairly good margin of safety there, I believe. So what we say for a 2x4 stud, 250 pascals is a good pressure limit to choose if that's your wall design. If you got a 2x6 wall, 500 pascal limit is safe at a 2x6 stud. That's 32 PSF. What's that? That's tons, thousands of pascals. So for every 20 PSF, we've got 1,000 pascals. So here we're about 1,500 pascals or so. So 2x6 studs saying 500 pascals I think is fine. 2x8 we say 750, and 1,000 pascals for reinforced concrete. We do have to be careful with concrete block. Concrete block that is, they're just sitting there basically without any reinforcing, can actually be knocked over relatively easily, and some of the failures have happened with concrete block walls. So if we have concrete block walls, we need to have some reinforcing in there, and they do need to be attached to the enclosure top and bottom. And if that's the case, that, and they're reinforced, that we're pretty confident they'll accept 1,000 pascals. If they're not, the concrete blocks are just sitting there, they'll probably handle 250 okay, maybe even 500, but more than that could be a problem. The other reason why concrete block is more problematic is that the fact that the walls, a 2x4 wall, will flex even a quarter of an inch or so, actually soaks up a lot of that pressure spike. It seems impossible to believe, but it's true. It soaks up about 40% of that pressure spike, so that we get about 40% more peak pressure with concrete block than we do with a typical 2x4 wall, which has a little bit of movement in it. Now, when I talk about studs, could be wood studs, metal studs, they act pretty much the same way. So the other design decision has to be made is comparing agents, and we can, using this calculator that I showed you earlier, throw in different agents and get an idea as to what size of vents the different agents would require. So there is a distinct difference between inerts and halocarbons, and they will actually produce roughly about the same pressure, but halocarbons require tighter enclosure. So once we tighten the enclosure down more, we find that the peak pressures come up to roughly the same values. Not quite. So here with FM200, on the negative side, we're running 337, 386, with Novec, 507 with a 40% inert agent. If we were at 38%, we'd probably be pretty close. So you can see that the interesting news here is that all of the most popularly used agents actually produce pretty close to the same kind of pressures when the enclosure is tightened up to the point where the retention time is roughly about the same. So the tightening required by the retention time is the big equalizer. If we put two systems in exactly the same room, a halocarbon and an inert, yes, the inert would produce a lot more pressure. But the fact of the matter is that we tighten up enclosures for halocarbons much, much more than we do for inerts, so that is the equalizer. Now, this is a design decision that I've used in numerous tests that I've done, where I show up and no one's even thought of pressure relief venting at all, and essentially the construction is finished, everyone's all proud of the fact that it's all buttoned up and it's nice and tight and all that kind of stuff, and I said, whoops, you've got a peak pressure that's a little bit higher than you probably would like, and you don't really have any venting for it. So what I've done in numerous situations is I've advised them to consider changing the isolation damper sequence that is often part of the HVAC system. So typically what happens is we close all the dampers, we isolate the HVAC, and then we discharge. So what I suggested there is, let's not do that. Let's discharge, or let's close the dampers towards the middle or the end of the discharge, so that we're actually using the leakage of the HVAC ductwork in order to vent pressure. And this is, I think, totally legitimate, and I like to say that this is a way to get a free pressure relief vent, and it can be substantial. And in most cases, changing the damper sequence is all that you need to do in order to get all the venting that you need. Now, this needs to be properly documented so someone doesn't come back and change the isolation damper sequence, that we're actually relying on these isolation dampers to give us venting, which also points to the fact that in most jurisdictions, the enclosure integrity, or the hold time, has to be checked annually, or at least the enclosure leakage has to be checked annually to see if anything has changed. And this is a really good time to look at whether anything's changed in the peak pressure side as well. Whatever dampers that you have in there, whether they be electronic, pneumatic, or gravity, need to be checked to make sure that they still function. There are 4 other ways to reduce the size of the PRV, or to reduce the need of a PRV altogether. One is to increase the discharge time, which I've shown you on the venting calculator. One is to decrease the concentration. So again here with, I guess the corollary of that is if you increase the concentration that the venting requirements will increase. So let's just go to decreasing the concentration. You notice it drops. It doesn't drop a whole lot. Raise the minimum humidity for halocarbons. Again, using the venting calculator, you can play with different humidities and see how they affect. So here we've got minimum humidity of 30%. So it's saying that we need 108. So if we change this to 10%, we see that rise dramatically to 206. So similarly, if we say that the minimum is not going to drop below 40%, then that dramatically changes the amount of venting that we need. See how incredibly dependent that the halocarbon is on the minimum humidity? Very dependent upon it. So it's a very important value to determine. And the inert regulating discharge valve, which will have the vent area requirement. I showed you that earlier for Pro Inert, and I can't recall the names that the different manufacturers use for the regulating valves, but that's kind of the way it's going as it is right now. So we've first of all looked at some options to increase hold time, or we looked at 7 options to decrease the size of the PRV for the NFPA folks, 7 options to possibly eliminate the need of a PRV. So let's look at 5 options to increase hold time. So one is to specify continuous mixing. Now let's just take a look at this on the little calculator here. And here we've got minimum protected height of 9 feet, and we've got a descending interface. So what we're going to do is we're going to change that to continuous mixing. And whenever we have continuous mixing, we need to have a minimum concentration. And typically what we'll do is we'll increase the initial concentration. Let's say in this case you increase it to 10%. And at this point, the maximum allowable leakage goes up to 1,753 square inches, which is, I think, 4 times what we had before. Continuous mixing in cases where you have a very high minimum protected height is the key design feature to put into the enclosure in order to decrease or in order to increase the hold time and allow for more enclosure leakage, if you want to put it that way. It's the only way that you're going to get protection for cable runs that might be at the top of the enclosure, for example. So if you want to protect the top of the enclosure, you must consider continuous mixing, and there's a bunch of different ways to do it. And it's often always assumed that there's a descending interface. I would say that at least 40% of the enclosures where descending interface is assumed, they're actually continuous mixing, but they didn't really look at the variables when the system was designed, and they weren't aware that continuous mixing in a lot of cases even existed. So it's often the way that we will pass an enclosure would be to allow continuous mixing, which could be keeping the HVAC system running, having dedicated circulation fans, or in some cases just allowing the equipment cooling fans to continue running during the retention period. Now, they're often running anyway. To learn more about this, whenever you test an enclosure, I recommend that you set the enclosure up to the hold time conditions and go around with smoke and carefully watch the airflow patterns, and you will probably see that you have a lot more mixing in there than you thought. Usually the cooling fans and equipment are strong enough on their own to provide continuous mixing. So here we have an example where we've gone from descending interface to continuous mixing. This is using Enclosure Integrity software, or I should say FanTestic Integrity software. We're not using the calculator, which is a lot easier, but you can still do the same thing. So here we show descending interface, estimated leakage area of that, predicted hold time 5.1 minutes. Here all we've done is we've changed to continuum mixing, the same leakage area, and we've gone to 13.9 minutes. So you can verify the same points with the Enclosure Integrity software, but it's more difficult. So the venting calculator that I showed you does these calculations backwards and a little bit easier to look at various scenarios. So here we have two options for getting continuous mixing. One is to keep at least one of the air conditioning systems running. If you've got a number of them in the room, then you probably only need to have one running in order to get continuous mixing. Pretty rare to have dedicated circulation fans, but possible. You could have them even powered with battery backup. You don't really need much in the way of airflow to get continuous mixing. So next thing is to compare agents. In this case, the inerts require less air sealing. Notice this example we used before. We've got 15 square inches on both of the helicarbons, which means that the enclosures are 2.5 times tighter. It does cost money to tighten up these enclosures, and it takes time. So that would be one of the things that you might consider in your design. The fact that the halocarbons can exist quite comfortably in a tighter enclosure is, however, good from the standpoint of the tighter the enclosure is, the less affected it will be by smoke events in other parts of the building. And I believe that protection from smoke is probably as important, in some cases more important, than protection from fire. And they're certainly much more likely. I think they're 4 times more likely to have a smoke event than a fire event, maybe even 10 times in some situations. So the fact that the halocarbons will happily exist in a tighter enclosure is actually a good thing. The next thing is extended discharge, which is pretty common with CO2. In fact, most CO2 systems I've seen do have a continuous discharge. They will put in an initial concentration and then an extended discharge that will match the loss rate to the leakage rate. So if we're leaking at a rate of 10 pounds per minute, then we discharge at 10 pounds per minute. And the assumption is that we maintain our initial concentration at all elevations, and extended discharge is always continuous mixing, and it is an option. You'll find this doesn't exist on the venting calculator because there's nothing to calculate. All that we do here with extended discharge is to calculate the loss rate, and as long as we keep continuously discharging at the loss rate, we can have a retention time for as long as we want, forever, 30 minutes, 2 hours, whatever. This is often added to enclosures that have large intentional openings, and so we keep discharging at the rate of loss to those openings, and that is something that needs to be considered. The reason why we run into these things is we will often have to make recommendations once the enclosure fails, and adding extended discharge is one of the recommendations that we could make. However, by the time you get to the point of testing the enclosure, it's often too late. And so we say, oh gosh, it's sure too bad that we didn't think about this in the design phase. So that's what I'm attempting with this, this venting calculator, is to get this figured out in advance. The next one is for particularly small enclosures, which are the single biggest problem that we have. Probably 40% of our tech support calls, I got a small enclosure, we've been air sealing it forever, we can't get it tight enough, and so on. Some of these small enclosures are absolutely tiny. They don't really represent a huge risk to the building. Sometimes they're next to a control room, and somebody can run there with a fire extinguisher in a moment's notice. So we do have to consider, in both NFPA and ISO, we do have to consider whether or not 10 minutes is the appropriate hold time. And I suggest for small enclosures of 250 square feet or under, 25 square meters, or under, that we consider a hold time different than 10 minutes. So by the time we get down to about 100 square feet of floor area, it becomes very, very difficult to get a 10-minute retention time, and a lot of cases 5-minute retention time is sufficient. So both standards say that the retention time shall be, or the hold time shall be 10 minutes, or a time required for response by trained personnel. ISO says unless otherwise specified by the authority. The authority usually doesn't know about it, doesn't know to specify it one way or the other, but this is something that can be thought about in the design phase. It's usually not. Sometimes a recommendation is made after we've spent weeks trying to air seal these tiny enclosures and said, look, how about a 5-minute retention time? Can you handle that? So the answer is yes. The other one is to measure the lower leaks versus the upper leaks, and we've already done a little calculation here where we've shown what happens when we change the lower leak fraction. We haven't changed the leakage. All we've done is change the lower leak fraction. We're at 0.25. We change it to 0.5, which is worst case. And we go to, I unfortunately can't remember what it was before, 1,111. So that's what it would be in worst case. Let's change it to 0.2. And we'll notice that we can have a much, much leakier enclosure because we are allowing leaks in the upper part of the enclosure, and we're keeping the bottom part of the enclosure tight to hold the agent. All these agents are heavier than air, so they do tend to accumulate in the bottom part of the enclosure, so that we can allow a leakier enclosure by reducing lower leaks. So here we show a little graphic that shows how the leakage rate of this heavier than air agent is actually controlled by the size of the hole in the bottom. It makes a little bit of a difference, the size of the hole in the top, but not much. But it's really the size of the hole in the bottom that determines it. If we cut the size of the hole in the bottom of the enclosure in half, we roughly double our retention time, or hold time. Not quite, but roughly. And here we show the same thing being shown in our software, which we showed in our venting calculator. It does the same thing. Here by changing the lower leak only, total leakage is still the same, just changing the lower leak. We've gone from 5.1 to 11 minutes. So here we show measure the lower leak and pass. So in this case, this is the total leakage. If we had total leakage, we've got to get it down to 15. If we have, if we measure the F, or the leakage fraction, we can go up to more than double that leakage and still have the same hold time. So the same thing is true for halocarbons as it is for inerts. So to answer your question, the first way, and the obvious way of doing it, is simply to seal off the suspended ceiling so that we are isolating the lower leaks from the upper leaks. So typically, enclosures tend to leak more above the suspended ceiling. They just don't put the effort into sealing up there as well. So in this case, we're covering the ceiling in plastic, and even though I've tested 300 or 400 rooms in my lifetime, I've only done this 4 times. And when you do it, you realize that it's time-consuming and fairly inefficient. Moreover, if you happen to fail, then you've got to pull it down to fix it and then do it again. Takes roughly about, for 500 square foot room, it takes roughly about 4 hours to do this properly. So that's one option. The other option is to use the door fan to measure the lower leaks, and here we have this apparatus that we pioneered, and it has 2 fans. This fan is measuring the lower leak, and this fan is doing nothing but pressurizing the above ceiling space so that we don't have any upper leaks in our measurements. So this one's taking care of the upper leaks, which we're not measuring. this one is taking care of the lower leaks. Now, often authorities get very upset when they see this. They say, oh my God, you know, or the plastic on the ceiling, same thing. They say, oh my God, you're covering up leaks. No. What we're doing is we measured all the leaks. Now we're just trying to find out how many of them are lower. Now, the other mistake that people make when they're running the software is they'll measure the lower leaks and they'll put that in as the total leaks, and that's a big no-no. I believe our training emphasizes that point. So the procedure is we first of all measure the total leaks and we see if it passes, yes or no. Then once we've measured the lower leaks, we now measure the leak fraction and we see whether it passes having measured the leak fraction. One development that we've had when we came out with this gauge, which is the DM2, is it has a set to zero function. So what we can do is we can set this fan to our test pressure, which would be 10 or 50 pascals, and then we set the other fan, this one down here, to zero, so that the pressure across the ceiling is zero. And what will happen is, as the fans are running, is they'll jockey back and forth until they come into balance. The old way that we did that was that we would lift up a ceiling tile and we put smoke there and see if the smoke went up or down. And you'd have, it was a two-man job, you'd have one person waving their arms and another person would be adjusting the knobs. It was very confusing. This system, all we do is we set the room to the pressure we want. We set the flex duct fan to zero, so we have a hose above the ceiling and one in the room, and we just let it balance itself out, which takes a few minutes, and then we take our readings. Works like a charm, actually, and on our new online training, we actually have Denelli doing a test in his office doing this particular test. So this assumes that this fan here is capable of blowing enough air to pressurize the above ceiling space. Now, obviously, if we look above the suspended ceiling and we can see 5,000 square feet of warehouse and so on, we're never going to pressurize that space. We have to be able to pressurize that space in order to neutralize the pressure across that ceiling so we can isolate the lower leak. So it's okay if that above ceiling space extends into adjacent offices, but we need to be able to pressurize that cap to neutralize the pressure across that suspended ceiling. There's a whole chapter in our manual on this, and it looks like one of those totally impossible type things until you try it, and then you realize it's not really that hard to do after all. And I can do one of these in 20 minutes versus 4 hours for plastic on the ceiling, and I've done them in 5, 10, 15,000 square foot offices, no problem at all. This model of fan here, for those of you that go way back to our 900 fans that we had a 20-inch duct. This is a 24-inch duct. The fans that we're using here are the 2 horsepower fans. They will blow a massive amount of air through this flex duct. So this is a variable frequency drive that we have down here, which does a magnificent job of pressurizing above ceiling space. We also can have a number of flex ducts going to the above ceiling space. I had one that you might see in our manual. I've got 4 flex ducts going to the above ceiling space. And it was an expensive test, but nowhere near as expensive as the alternatives, of which there weren't any. So this is a great way of passing enclosures that wouldn't pass in any other way. The other thing about this is that these 2 systems here can later be broken down into 2 separate systems that can test 2 separate enclosures. Then you can bring them together with what's called the leakage split kit, which is this flex duct and this little panel up here to do the ceiling neutralization test to measure lower leaks. So someone said that's awesome, and yes, it is. It's awesome. Works great. Here's a schematic. This one is configured a little bit differently. Here we've got the flex duct on the lower fan. We find a lot of cases if the ceiling is relatively close, that it's better to run the flex duct like this. Otherwise, it hangs down in a big old sausage here. If the ceiling is really high, we might want to put the flex duct in the upper fan. Works great both ways. So let's just take a look at this. Here we've got the flex duct going to the upper fan, and we're depressurizing. And it's important that these fans both blow in the same direction. If you've got one blowing, one sucking, it doesn't work. So here the lower fan is measuring the lower leaks, and all this air that's leaking into the room is being handled by this fan. The leaks from the upper fan, or the leaks above the suspended ceiling, are coming in through these holes, going in through the flex duct and being exhausted. And if the pressure across the suspended ceiling is zero, then they're both taking care of their own leaks, so to speak. If there is a positive negative pressure across there, this fan will be reading either too high or too low. There's another picture of the flex duct mounted in the upper fan. This is one of our really old systems from about 10 years ago. Now, the same methodology, same technique can be used for subfloor only testing. So here we have subfloor only, where we've sealed off the floor and we can't seal off all the leaks. So what we do to neutralize the flow across the floor is we pressurize the entire room. So here we have a fan in the floor that's measuring the subfloor only leaks, and a fan in the room will be making a pressure which will be pressurizing the room to get the pressure across this, I call this the walk-down floor, to zero. And the fan that's pressurizing the room, again, will set it to zero between the room and the subfloor only. And this one is measuring the pressure, or is measuring the flow that's required to pressurize the subfloor to either 10 or 50 pascals. NFPA and ISO don't specifically say that you can do this. They say that the procedure is meant for total flooding, but I can tell you that thousands of these tests have been performed. The other reason or way that this can be utilized is that we can measure, effectively, we can measure the lower leak in the enclosure by measuring the leakage below the subfloor. We can then measure the room leaks and come to some conclusions about where the leaks are in the room, and we can utilize this for both ISO and NFPA for determining the location of the leaks and by coming up with a value of F. I don't want to get into that in a lot of detail. If you have a situation like this that comes up, we usually kind of walk through with our tech support and get it sorted out. Sometimes the authorities are concerned about what's going on here. In cases like that, we'll take a look at how they're testing, make sure they're doing it in the right method, and if they are, we'll assure them that what they're doing is fine and have them go ahead with it. If you have any questions about the cost of this or that, just send an email to sales@retrotec.com and we'd be happy to send you a quote. If you've purchased training from us before, in some cases we have credits for what you've bought before, depending on what you bought and when you bought it. We're trying to be as reasonable as we can with the cost of our new training and software and so on to get as many of you on board as possible. I think in the US we've got roughly about 40% of the people converted, and we're just starting to work on the European contingent. We've been working with a lot of the manufacturers to add some of their formulas for peak pressure into our equations and to add new agents. I think we're going to be getting aerosols in there soon, and we keep upgrading the software and so on. The version of the software that you see right now is brand new, built from scratch. It took us about 2-3 years to develop it stunningly. So let's take a look at some design tips. The first one is you don't really get any credit for this, but it's kind of obvious. If we're trying to keep the pressure in an enclosure down to, let's say, 250 pascals, we don't really want a vent that opens at 250. We want a vent that opens, I like them to open at about 80 or so, not much more than that. And that allows us to vent early, and this shows the idea. This is just kind of a made-up graph, but it shows the principle. So if we wait to open the vent until it hits 250, it's going to rocket right by it, because these spikes are really, really fast. They're, for inerts, they happen in 1 or 2 seconds. So you almost don't even have time for the vent to open. If it opens late, you start to accumulate mass in the room, and the more of that that you can vent, the shorter the spike is. First point. Second point, vent high. So I think most vents are put in the upper part of the enclosure. The higher you get them, the better. A thing to consider here is if this is a suspended ceiling, when it vents through this vent, the suspended ceiling has to have the capacity to allow the vented agent to go through the suspended ceiling. For, let's say, a 40% inert discharge, we're going to lose around about 30% of that total volume of the room during the venting phase. So that's a lot of airflow in a very, very short period of time. And if you don't allow for sufficient venting in the ceiling, you will disrupt and blow the ceiling tiles out. So we have a formula in our training course that shows how to determine what the pressure drop across the suspended ceiling will be. I like to keep it down to 50 or 100 pascals maximum. So if we have, let's say, 500 pascals peak pressure across the enclosure for 1 square feet, then we need to have about 10 square feet of opening in the suspended ceiling so that we keep that pressure down to about 50 pascals. So along with venting as high as possible, we do have to watch the suspended ceiling. The next one is that no matter how big your vent appears to be on paper, it may not be venting as much as you think it's going to vent. So there's 2 factors here. This one is, like we mentioned earlier, at what pressure does the vent open? Second is, how much free vent area does it actually have? And the manufacturer's numbers are usually kind of close. Some of the manufacturer's free vent area is true as long as the pressure is up to a very, very high value. So what I do if I'm using a vent, I take it and I slap it in a cardboard box and pull the negative pressure on it, because you don't want to blow air at the vent itself. And I negatively pressurize the vent up to, let's say, 100 pascals, and I see how open it is. Open it, pressurize it to 200 pascals. I see how open that vent is. In the case of pneumatic or electronic vents, you can measure the resistance of the vent, but of course they're not actuated by pressure, they're actuated by electronic or whatever. So certainly measure the vents. The other thing is that the vent path may be ductwork or whatever, and you need to measure the entire vent path so that whenever we're doing an enclosure leakage measurement, we want to measure the enclosure leakage for hold time, then we want to set it up for venting and measure it again. I won't get into that in a lot of detail here, but that's something that needs to be considered. So does it open partially, or does it open too late? Is it blocked? In this case, we've got a flap on the back, can be easily blocked. So on your annual inspection, you should measure the venting pathwork to make sure it's still working. You should be measuring, or you should be checking the electronic dampers to make sure that they open. They may not. A lot of cases the vents are installed backwards, so if they have a halocarbon, they assume there's going to be a positive pressure, and they really should be venting on the negative side. So that's something to watch. So here's the point that I was making about venting the suspended ceilings. This particular problem may have caused by venting going from the enclosure up to the suspended ceiling, up through the suspended ceiling to holes above it. It could also be caused by the velocity of the agent hitting the tiles. Looks to me like this particular one is caused by there not being any honeycomb tiles in the suspended ceiling. So they kind of learned that lesson. And here I've shown you a funky little formula that allows you to determine how much open area we need in the suspended ceiling in order to
prevent this from occurring. So that needs to be considered. Something that definitely needs to be considered in the design phase. If you're testing it, that would be something that I would point out. And the next one is to run the enclosure calculations during the design. This was an earlier version of the venting calculator, similar to what we were looking at earlier, but it is evolving, and by the time you get it, it should be in pretty good shape. So it's primarily revolves around the size of vent that you need, because that's the design consideration that you need to make. As far as the enclosure leakage is concerned, you will notice that as you change parameters that you require less and less and less enclosure leakage, which becomes more and more and more difficult. Unless you've got experience with how tight these enclosures can be made, you don't recognize, let's say for example, if you've got a small room and if you've got the minimum protected height at 90% of the room, that it may be impossible to get that room tight enough. Let's just go back here. So when we run the enclosure calculation during the design, we have to consider a bunch of factors. One is increasing the volume. So all things being equal, when we increase the volume, we increase the retention time. So we can have more leakage, we've got more agent to get lost, and you can run these in the venting calculator as well. And it's a really, really fast way using the venting calculator to see that as we put in more volume of agent, that we can have a leakier enclosure. The next one is to keep the protected equipment as low as possible. The problem enclosures occur when we're trying to protect very, very close to the what we call the maximum. This says maximum protected height. I prefer the term maximum flooded height because we're not really protecting to this height. We're only flooding to that height, and for the sending interface it's going to drop in time from that very quickly. So I don't like that term. Minimum protected height is a term that's stuck, so it's okay. So here we want to keep the minimum protected height, this value, as low as possible, keep the equipment as low as possible, which will much more easily enable us to protect it. The higher it gets, the harder it is to protect. Unless we use continuous mixing, as I talked earlier, then it doesn't matter. Well, here we got, this is our new online training. Some of you might have gone through this. The level that we're talking about today is really for the authority having jurisdiction, the fire protection engineer, and also for the tester. The tester should know that. We asked them to go through that section as well. And so now we're going to jump on witnessing. We've got a little section on witnessing. So let's just take a look a little bit about, we give you a certificate. Our certification's been pretty much accepted worldwide for the last 25 years or so. I was the one who came up with this idea in the first place of doing this kind of testing. I've written the bulk of the text of most of the standards, so people figure that, you know, probably after 25 years I might know something about it. If someone has a specific question or there's a concern that authority has, I've usually always been able to work through and with both the authority and the tester and come up with something reasonable that makes sense. We've got people pretty much, we've got certified testers all over. I think we've had about 3,000 at one point for the old certification, and we've got just touching on 1,000 for our new certification, but we pretty much blanket the globe. Our website will start listing the people that have our new certification only, and I think we've already eliminated the old certification, and we're changing it so that it has to be updated every 3 years, which is pretty typical for the industry. So in 3 years' time, we'll have a lot more information and reconfigure the training course once more. Here we have the old CA2000 software, which has more or less the same calculation, except it has no peak pressure analysis, and for that reason it's no longer in conformance with any of the standards. So we've been getting people up and running with our new FanTestic Integrity software, which is a different look. We'll just show you real quick here. So this is what our software looks like when we run a test. We have the ability to take each section of the test and collapse it down, so it's kind of a nice, neat little package. We don't have tabs, and the software can run continuously down so that we can expand it out and keep doing test after test after test, and it's all can be one continuous strip. The other thing that it does, which I think is pretty nice, is that creates a report in Word that can be customized. It pulls all the data in. You can put in pictures and any text that you want in there. Put your company logo on there and all that stuff. And whenever you generate a report, you just click Generate a Report. It generates it in Word. You can go in there and clean it up a little bit and reduce the reporting time down from what is typically for us probably 2 or 3 hours. You can reduce it down to about 15-20 minutes. So I think it's a great feature, something that you should try out for sure. And if you have some problems doing the customization, by all means let us know and we'll walk you through that. So I don't want to get too involved in that. We're 20-some minutes off 2 hours, so we actually have another webinar going on at 11. So this is the software that is conforming. Equipment always has a gauge calibration verification report. We've been updating those and trying to make them a little bit more readable, and it shows the different standards that the gauge complies with. There's another one for the fan, which is here, which shows the performance of the fan and whether or not it conforms, and we have a specific test that we use for the enclosure integrity. Then we have the field calibration check, which typically is done with a hole that can be created above the panel, so that I have had authorities ask to see the equipment measure that hole, and so that's something that they can ask for. I also recommend that you do a field gauge check, so that you can just take 2 of the ports of the gauge, connect them together, see if they read the same thing. Something you should do on a regular basis. There's a lot of information we have in our videos on our website to show you how to do this. This is encouraging the authority to make sure that there's an even pressure field across the room. In this case, the pressure across this wall is only 6 pascals. This door needs to be open, something you can do quite easily. Walk around the enclosure with the pressure gauge and poke a probe underneath all the doors. I'll normally do that with the fan running to make sure I have a complete return path. And the authority can also verify that the numbers they saw on the gauge were the correct ones. A really important feature is to make sure that the equipment is on the right range, and on the enclosure leakage test, when we go to select range, you'll notice there's a picture of each range, and this is probably the most common mistake that people make, is they say they're on one range and they're really on another. So the authority is going to witness one thing. Making sure that they're on the right range is probably the most significant thing. So if they say they're on this range, but they're actually on this range, then that would change the retention time by about 600%. So clearly that's one of the most important things. That's why we show you pictures, so that you can observe what's going on. And there we go, range selection. There is a section in the standard in all of them that allow for both plastic on the ceiling, and the Flex Duct test is specifically named in the NFPA standard as plastic on the ceiling test. So yes, it is allowed, and no, it's not cheating. And it's talked about more generally in the ISO standard, not done as often, but it is just as allowable. There's a section in there on that allows for the measurement of the leakage split, or the F value. And then there's an entire enclosure integrity verification form that we supply with our level 1 training course, And it essentially shows you 21 questions that if you answer those questions, you have a 90% or better chance that the test was done properly. All you do is just go through them and answer them one at a time. There's a guide that goes with this that tells you exactly what to look for. And even if you've never seen a test before, if you take this form and you fill it out and you follow the guide, you have a very, very good chance that the test has been done properly. I think that's the end of the presentation. So thank you very much for listening, and bye for now.